I'm Hemashri, and welcome to this video where we dive into one of the core parts of embedded systems, the GPIO configuration, specifically the concept of pull-up and pull-down resistors. This video is designed to walk you through the same logic implemented across different platforms, starting with Arduino, moving into ESP IDF, and briefly touching on FreeRTOS. Whether you are a beginner or someone looking to strengthen your fundamentals, this video gives you a clear side-by-side understanding of how a basic electrical concept translates into real code and hardware behavior. Let's decode GPIOs from theory to toggling real pins. Let's begin. So imagine a kid holding a balloon. If no one pulls the string down, the balloon goes up. That's what you pull up. But if someone is holding the string down, it's like a pull down. So GPIO pins are like that. They float if left alone. So in microcontrollers, every GPIO pin can be configured as either input or an output. But when a pin is configured as an input, and if you don't connect anything to it, it enters what we call as a floating state. A floating pin doesn't know whether it should read high or low. It becomes sensitive to electrical noise, static changes, or even your finger coming close. In this state, it can randomly fluctuate between 1 and 0. That's the problem. For example, if you are using a button to trigger an event and your pin is floating when unpressed, your code may behave unpredictably. Sometimes it might think that the button is pressed even when it's not. To solve this, we connect the input to a fixed logic level using a resistor. That way, the pin always has a default or known state when the button is not pressed. With the pull-up, we connect the pin to VCC, typically 3.3 or 5 volts, through a resistor, so it's high by default. With the pull-down, we connect the pin to the ground through a resistor, so it's low by default. All right, now let's see this concept in action using a simple walkway simulation. So we are using an ESP32C3 Mini 1 port and a push button and LED and a resistor which is of 1 kilo ohms. And so let's see what happening in this setup. So the button is connected to GPIO6 and we have enabled the internal pull-up resistor in the code means when we are not pressing the button, the pin stays high by default, and when we press the button, the pin gets pulled down to low because the circuit completes through the ground. So let's see the simulation to understand this better. So you can see that when the button is not pressed, the LED is glowing. So when I press the button, it gets off, and when I release it, it's again on. So So here imagine a situation where if you don't use any resistor, then you are basically giving the GPIO pin no clear voltage to hold on to. This makes the signal float randomly when the button is open. The pin might read high or low unpredictably. And if you wire it wrong, let's say VCC directly to the ground, over time it can cause current spikes, heating, or even damage the microcontroller. You may not see a dramatic boom, but after repeated use, you could smell the burning plastic or hear a soft zap and your board crying for help. So be kind to your microcontroller. Use that resistor. It's a small piece and it can help for a long life. So common pull-up and pull-down resistors are typically between 1 kilo ohm to 10 kilo ohm. Many microcontrollers can also have internal pull-up and pull-down resistors that what we have seen right now in the code. We have enabled the pull-up in the code itself. So you don't need to add any external components unless required. So until now, we have used Arduino IDE for simple button and LED control. It's beginner friendly and abstracted. But when you are working with real time systems or need tight control over memory, performance, or multitasking, ESP IDF toolchain is the way to go. Now let's talk about FreeRTOS. ESP IDF comes with FreeRTOS built in. So FreeRTOS stands for Free Real Time Operating System. It helps manage multiple tasks on the microcontroller efficiently. Without RTOS, you write everything in a while loop, the blocking delays and all. With FreeRTOS, you can run multiple independent tasks, each with its own priority and scheduling. You can pause, resume, or delay them without affecting others. It's like giving your ASP32 multitasking powers, just like your PC runs Chrome, Zoom, and File Explorer together. So let's dive into this code. Find the GPIO pins. The GPIO number 18 controls the LED and the GPIO number 36 controls the button. So these macros are defined in the driver headers and give clarity over using plain numbers. Here it enables a physical pad for GPIO 18, then sets it as an output pin so that we can control the LED. We create a structure to configure GPIO 36 pin for the input mode. So we are masking it to get the pin number 36 and we are using input mode and we enable the pull up internally in the software and we disable the pull down and we right now we are not using any interrupts. But you can use pause edge to fire an interrupt when the button is pressed, more efficient than polling. Here we are inverting the logic because with pull up, if the button is pressed, the LED goes low. And if the button is unpressed, the LED goes high. And here it is here V task delay. So it is a free RTOS function used in ESP IDF to pause the current task for a given amount of time. Unlike delay in Arduino, which blocks everything, V task delay, this only pauses your current task, letting other tasks to run in the background. So let's see the simulation to understand better. So in default, the LED is on, but when I press the button, it goes off for that particular time. And when I release it, it again goes on. Now let's look at the pull down configuration using Arduino IDE on the SP32C3 Mini. When a digital input pin is left floating, it can pick up random noise and give unpredictable readings. To ensure the pin reads a low when the input is unpressed, we connect a pull down resistor between pin and ground. So here, the button is connected between GPIO 8, that is D4, and 3.3 volts, as you can see in the image here. A 10 kilo ohm resistor is placed between GPIO 8 and the ground. When the button is not pressed, the pin is pulled to ground through the resistor and reads low. When the button is pressed, then the 3.3 volts is applied directly and the pin reads high. And when I release it, it goes off again. So this gives us a clean digital signal without bouncing between undefined levels. But the difference between the pull up and pull down in previous screen versus this is we have used an external resistor to connect between switch and the ground. In this setup, a push button is connected between GPIO 36 and 3.3 volts. A 10 kilo ohm pull down resistor is connected between GPIO 36 and ground, and an LED is connected to GPIO 18 with a current limiting resistor. Is the entry point for the free RTOS. Unlike Arduino's setup and loop, here the control starts from this function where we can launch tasks or run forever loops. The interrupts are disabled as of now, where we are using this polling concept where the microcontroller constantly checks whether there is any change that has happened in the GPIO pin or not. And coming to the loop, where we said that if the button is pressed, the LED goes on, and if it gets released, it goes off. And we have also added the delay. Let's wrap up everything we have explored so far. So we started with the basics of GPIO input configurations, pull up, pull down, and we saw how both methods work practically using Arduino IDE and ESP-IDF toolchain. We have learned how microcontrollers communicate with pins using internal registers, input sensing, and output driving. And the free RTOS adds power like non-rocking delays, task management, future-proof structure for multitasking and real-time performance. I hope the video is interesting. Thank you.